This is lesson 34, VHDL example 19. And in this example, we'll design a binary to BCD converter for any number of bits in the binary number. And to do this, we'll use for loops. Now remember our shift and add algorithm that we had in lesson 32, where we shift the binary number left 1 bit, and if 8 shifts have taken place, this shows an 8-bit one, then the BCD number will be in the hundreds, tens, and units. And you remember, if the binary value is greater than 5 or equal to 5, then we add 3. And we showed how this went for a 8-bit number, FF. We went through those details. And we showed how it went for the 6-bit number using this algorithm, where we clear all the bits in Z, shift B 3 bits to the left, and then do, in this case, 3 times, and add our algorithm. If the units is greater than 4, then we add 3. So let's see how we can write a VHDL program to do this. Here's the binary to BCD 6 for this 6-bit case, say of 3F. And this is what we end up with as a circuit. Well, the entity will be B, 5 down to 0. Here's 5 down to 0. And P, we need to go 6 down to 0, because the answer 63 would be 6 down to 0 is the minimum that we need. Then in the architecture, we'll define the variable Z inside this process, where we're going to put the binary number in. So the variable Z is 12 down to 0. You see, Z here needs to go 12 down to 0, because that's where the answer will fit in. Now, in the architecture we have begin. You remember the first thing we have to do is set Z to 0. Well, we can do that with this little for loop. For I in 0 to 12 loop, Z goes 12 down to 0, Zi, remember Z is a variable, so we got colon equals 0. So you go through here, setting each bit in Z equal to 0. The next step is to shift B left 3 bits. Well, that ends up being Z 8 down to 3. Here it is here. 8, 7, 6, 5, 4, 3 just gets B, which was 5 down to 0. So that shifts B left 3 bits. Then we've got to go through this loop 3 times for the next 3 shifts. So we can say for I in 0 to 2 loop, so this is going to go through 3 times. And we check the units. Well, the units is Z 9 down to 6. 9 down to 6 is the units. So if the units is greater than 4, then we just want to add 3. We can just say Z 9 down to 6 is Z 9 down to 6 plus 3. That will put in a little adder. We'll talk about adders later in detail, but we can just do it with a little plus sign here. Then we have to shift Z left 1 bit. Well, to do that, we just set Z 12 down to 1. 12 down to 1. Make that the same as what Z 11 down to 0 was. So 11 down to 0, if we make that 12 down to 1, that's the same as shifting Z left 1 bit. We just do that 3 times, and then the answer P will be Z 12 down to 6. You see, 12 down to 6 is the same as P 6 down to 0. So P will then contain the 63. Now we can test it by simulating it. Here we made the counter increase by 3, so we end up with 3F over here, and sure enough it's 63, and the P just goes 0, 3, 6, 9, 12, 15, 18, 21, 24, and so forth, incrementing by 3 all the way up to 63. So it works. Well, what would we have to do to make an 8-bit one? We went through this 8-bit one to check it out back in lesson 32. All we have to do is change B now to 8 bits, 7 down to 0. P will need 9 down to 0 to contain the 255 maximum, say. And you remember we went through this So let's see what we have to change. Z now is 17 down to 0. You see we need 17 down to 0 to get this whole 255 in there. So we go for I equals 0 to 17 loop. This sets all the bits in Z to 0. Now we have to shift B left 3 bits. Well, that's going to end up being Z 10 down to 3. 10 down to 3 gets B, which was 7 down to 0. And then we have 5 bits left to shift after shifting 3 bits. So we need a for loop to go through 5 times. So for I in 0 to 4 loop, we'll go around 5 times. And we first check the units. Well, the units now are Z 18 down to 8, 11 down to 8. So here's Z 11 down to 8 is the units. If that's greater than 4, then we set the units equal to units plus 3. Now we have to check the tens. Well, the tens is Z 15 down to 12. So if Z 15 down to 12 is greater than 4, then we add 3 to it. And then we have to shift Z left 1 bit. That's Z 17 down to 1 gets 16 down to 0. That just shifts Z left 1 bit. And we do this 5 times, and when we're done, the answer P is in Z 17 down to 8. And that will contain the 8-bit number. And we can check it by doing a simulation. Here we make B go incrementing by 25, it looks like here, 5, and then 1E is 30, 37 hex is 55, and so we get 80, 105, 130 until we get up to FF, and sure enough it's 255. So the 8-bit one works. Well, you could do it for any number of bits. You could also make a top-level design. Suppose we take this binary to BCD converter. The output was P9 down to 0. We can add 6 more zeros to X and display the switches, put a hex value into the switches, and on the 7-segment display the corresponding decimal number. Here's what the top-level entity would look like. We've got the clock coming in, a button, this should be really M clock, switches, LD, A to G, AN, and decimal point, and the component binary to BCD and X7 seg B. So now we put 2 components in the architecture, and then after the word begin we have these 2 signals, X 15 down to 0 and P 9 down to 0. We'll concatenate these 6 zeros in front of P for X. The switches go to the LEDs, and then we just port map the binary BCD. The B gets connected to the switches, P goes to the signal P. Then in the X7 seg, X, which contains that P, just goes to X. Clock, these should be M clocks really, goes to M clock. Clear goes to button 3, A to G, AN. So that would be a top-level design. You could check that out and see how it works. Here's what a 16-bit binary to BCD converter would look like. You could put in, FFFF here and get out, up to 65,535 out. The B then would be 15 down to 0. If you drew the picture, you'd see that P would be 18 down to 0. Variable Z is now up to 34 down to 0. And now you, again, same algorithm, set all the Z's to 0. This goes 0 to 34. Shift B left 3 bits is now Z 18 down to 3 gets B. And then, since you've shifted 3 bits, you've got 13 bits left to shift, so now you need for I equals 0 to 12 loops. You're going to go through this another 13 times. You first check the units. The units are now Z 19 down to 16. If that's greater than 4, you add 3. Then you check the tens. The tens is Z 23 down to 20. Add 3 if it's greater than 4. Then you have to check the hundreds. The hundreds is now Z27 down to 24. Then you got to check the thousands. That's Z31 down to 28. Now you don't have to check the 10,000s because the biggest number will be 3 before you shift it the last time to get a 6. Remember, 65,000 is the biggest. So you'll never have to check the 10,000s. But you do have to shift Z left 1 bit. That's going to be Z34 down to 1, gets Z33 down to 0. And when you're done, the P is just going to be Z34 down to 16. So you can do any size B you want. It just changes the limits that you have for Z and for P. And here's the simulation for the 16-bit to see that it works. Here's 0, we're incrementing by 8,000 here. And so FA00 is equal to 64,000 decimal. So these binary to BCD converter programs are very useful to change a hex number to the corresponding decimal number.